One of our colleagues came up with a question after he saw my presentation. He asked, can one use combination of premixed and diffusion burners to obtain low emissions of mild combustor? So, we must first understand the way mild combustion process works and how it differs from the conventional combustion process. Am I to understand people know about mild combustion or no? Okay, so I will spend some time showing what mild combustion is. See, in a conventional diffusion combustion process, the burning fuel jet in, let us say, in quiescent air will have all the temperature values from ambient to the flame temperature. You have a flame, you have ambient temperature inside goes to 2000 and odd K, and therefore you have all the temperatures present inside. And if the flow were to be turbulent, there will be local density and pressure fluctuations that are not really small. That is why whenever you have a turbulent flame, you will find a sound, and that sound gives you healthy situation of the flame, if you may want me to think so. But then this is the one which gives rise to noise, because noise is essentially because of pressure fluctuations. And NOx emissions are also not so small, because they get generated in the high temperature flame zone. When temperatures are high, you know it is function of e to the power of E by RTB, also related to p to the power of oxygen half and so on. So, you know that you will get higher NOx at higher temperatures. So, in fact, to minimize the NOx emissions as well as CO emissions, the standard rule is that you must walk through a temperature range not far beyond 1900 K, perhaps closer to 1700 K, to make sure that both the NOx and CO are within limits. And as I mentioned, the NOx is related to essentially Zeldovich mechanism, which we discussed in the earlier lecture. Okay, I will tell you about mild combustor. From one of studies, what you see here is this: you introduce fuel and oxidizer by keeping them separate, you do not mix them at all. So, you have fuel inlets here, oxidizer inlet here. Bring up the combustion system to high temperature, say more than 1000 K. Now, as it is operating, reduce the exit area to a level such that the flow recirculates within the system. Now, please do not worry about the presence of this, it does not have to have this, without that also it works. So, the flow recirculates, the flow that goes out recirculates here, because you are reducing the cross section here. So, this hot gases recirculate, dilute the high speed jets of fuel and air, so that their temperature increases, but fuel and oxidizer quality comes down. You see here you have fuel jets and oxidizer jet. I have shown this to be small because the flow rate of fuel is small compared to oxidizer, and the hot gases which are around, because of the high injection velocity of this oxidizer or fuel, the gases will get into the system, and this causes mixing, and as it goes up you will discover the oxidizer will get diluted, so also fuel will get diluted. But then the heat that present there also mixes with this and gives you increased temperatures, and when the temperature crosses about 1200 K, you will find most reactions begin, and this is called a mild combustion. This mode gets established. The temperature becomes roughly uniform within about 100 to 100 K or so, and the combustion becomes virtually flameless, and the acoustic noise goes down. I think experience is also there at IIT Madras on this. The noise goes down because there will be less pressure fluctuations. The key is that not to have wide temperature change in the combustion process. The trick is that they have introduced the burnt gases mixing with that, so no reaction can take place, only mixing can take place, increases the temperature, reduces the fuel fraction and oxidizer fraction. They come up to a stage where at that temperature reactions go on, and you will get the whole combustion process. So, you will find that in the range of oxidizer fraction and temperature of reactants, there is one normal combustion at 18 to 20% oxygen, and if it is, you can also get hot flames if you use reactants which are higher temperature, and this is the mode where there is a flameless combustion. If you increase the oxygen fraction much more, you have called oxy-rich flames, and this is one mode which is used in the industry, okay. Particularly when you want to melt steel or do things like that, oxy combustion is used. If you look at a comparison of different strategies taken from literature, you will discover you have 4 cases. Lean premixed. Let me explain why this lean premix is used, because related to the question which was posed. I can go lean and mix it, premix it, so that the combustion process is clean, no diffusive combustion. So, there is one mode which is competing with mild combustion in terms of pollution reduction, emission reduction, particularly NOx. So, lean direct injection, this is also a possibility. Rich quench approach to the process of combustion. Then the flameless based, which is what mild combustion is about. What is shown here in terms of the parameters, combustion efficiency is high, this is also high, 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 all of them have high combustion efficiency. If you are looking at combustion instability, roar, whatever it call as roar, it is high in lean premixed, we will see why it is, low here, low here, low here. Fuel flexibility, you want to use mostly gaseous fuels in all these studies. The question is it fuel flexible? Well, in this case it is stated to be moderate, high, high and moderate. Mechanical complexity is moderate, the lean direct injection is high because you have to raise the pressure and inject it, it is moderate in the ASS. NOx emission is low, low, moderate and is stated to be ultra low. This is taken from a literature, and you have many other features comparing them. The key issue is that the flameless based combustion system is supposed to be ultra low compared to lean premixed. Well, this is a question which bothered me for last few days, and when you look at literature, you look at aircraft engines, you hardly find any literature of the kind which you think to compare the results. In aircraft engines, there is a requirement for limiting NOx, and all the developments on the premixed combustion systems which have taken place in the last 15 years is arising out of the need to reduce the emissions both for aircraft and power generation packages using natural gas, and in the case of aircraft it is jet fuel as the fuel required for the operations. So, with this situation, if you look at the literature, you will see that the NOx that is allowed for is a function of pressure, and they always talk about little cycle which gives you NOx, and on that measure one engine is qualified compared to the other. So, you will discover the large amount of data on premix systems is for aircraft, and the combustion system design is centered around reducing the specific fuel consumption because you want to operate it in a lean mode, and that is why it is so. The NOx also depends on operating pressure ratio, do see that it is pretty linearly dependent on that. So, when you want to compare data, you must be very careful because the data related to aircraft is at pressure, the data related to industrial combustion systems most likely is at ambient pressure, and very strong dependence on pressure is what you see here from 120 to almost like 20 atmospheres, a very large reduction. So, when you go to 1 atmosphere, it may will do the job. That is a lean premix system may do the job, that is the hint that you get from this. But I try to see if there are any data in premix combustors to look at NOx. There is not enough data either on mild combustor in comparison with that of premix systems to say that there is firmly one or the other is correct. And I thought it was very easy to locate, it was really not possible. It looks surprising that why is it you have premix combustor and you do not measure NOx at various ratios of leanness or whatever, it does not seem to be available. So, if one system The only argument why mild combustor seems to be superior is what I found in an argument is that the safety of a non-premixed arrangement, providing industrial safety as the criterion for the choice of mild combustor, it may be a reasonable choice. I think there is a distinct case to create a safe premixed combustor which gives the same level of NOx as mild combustor. In a way, I am actually disagreeing with the situation, low for lean premixed and ultra low. You may ask me why, so we can subject it to a little discussion. The argument that I made was when you look at a mild combustor, you are pushing in some fuel and oxidizer in some ratio and you are taking it out on the exhaust. There are a lot of dynamics taking place inside, let it take place. It is not my problem to find out what happens inside. You look at a temperature that comes out of the combustor, which may be close to the premixed temperature, because it is well mixed, there is enough time for combustion to take place, and what you get out it must be close to premixed flame temperature for that mixture ratio. And you take a premixed combustion system, you are doing the same. And to say that the conditions are very different, there is no lateral change of a condition when you look at a premixed combustion system. There is a variation of the temperature going from the premixed state, from the initial condition to the flame temperature. There is a sharp domain of the flame thickness. So, I can't find enough arguments to say why a premixed combustor cannot perform as well as a mild combustor, and I do not find any data in literature that I can lay hands on in the last few days to say one thing or the other. So, I leave this question at that point, and there is some opportunity therefore for somebody to do research, to do one thing or the other, because there is too much of hype around mild combustors. In some ways I am a part of that. I was there in a lecture in international symposium when a German person presented it. It looked exciting. So, Sudarshan Kumar, who is now a professor at IIT Bombay, did his PhD on this subject. But I no longer am able to defend that position at this moment. I am being honest with you, and therefore, there is some case for doing a careful study on this subject. Okay. Yeah. I will switch over to a question was asked by Kalyani. Tell me something about, he did not ask this question. He asked, you talked about G parameter in the erosive burning. How did you uncover that? What is the basis of that? Then I thought I will just present the paper and show what is what. Then I discovered that I can enhance the knowledge value little more by including what happens in hybrid rockets. So, I picked out this commonalities between erosive burning and hybrid rocket motor burn rate. Hopefully, we will answer the question. So, in the case of erosive burning, what you have is a system here which produces hot gases, and hot gases pass through this. We know how much is going through, at what pressure, and you measure the burn rate here, and you know the flux and the burn rate, and so you get the erosive burning component. I brought it up in an earlier presentation as well. In a hybrid rocket motor, what would you have? You would have a fuel block with a port, then you have an oxidizer coming in. In this case, what is being shown is N2O, nitrogen oxide, but the flow through this will create essentially a boundary layer next to the wall, cause heat transfer, cause fuel vaporization, mixing, combustion. That is how it happens. This behavior and this behavior are not very different. Only difference here is, even if the propellant gases are not going there, if you ignite it, it will burn on its own. That is the difference. Here, if you do not have oxidizer, the fuel will not burn on its own. But therefore, the burn rate of both these will be influenced by convective flow of gases. I switched to erosive burning, taking on from the paper, and I also mentioned this Lenoir and Robillard, which is like this. The burn rate, this is the non-erosive part which we have been looking at over a period of time, and this is the contribution due to convective flux. The G is the mass flux, alpha is a constant, and L is a length scale, beta is another constant, rho p r, which is the same thing as the burn rate here divided by G. This part is related to what is called blowing effect. I must explain to you what blowing effect is. When you transfer heat from the boundary layer to the surface, it vaporizes. Suppose vaporization is much more, what happens is it pushes away the boundary layer, and because it pushes away the boundary layer, the heat flux comes down. This is called blowing effect. So, you must account for this blowing effect. There is a way of accounting for it by using analysis, but its behavior is expressed through this route. I must tell you, after all this is still a most elegant piece of work, the work of Lenoir and Robillard. Now, this constant alpha is expressed in his own paper in this manner. So, until this there is nothing new that has been done. Okay. What did I do? If you may ask me, I said, okay, let us define eta as R by R naught, and whenever there is an R naught, we will multiply by rho p, because it is the mass flux which counts and never really the actual linear regression. So, eta is equal to this. I have put together a quantity G naught, which is here, mass flux by rho p R dot. See, this burn rate changes because of pressure. Mass flux also does something to burn rate. This ratio is important, because if G is 0, it depends only on pressure. If G is present, it will be additional flux and therefore burn rate. So, this parameter therefore is a natural choice. So, G naught to the power of 0.8, and you put together other things, you will get a small change of Reynolds number, and this parameter due to blowing effect is also present here. Then you follow through some analysis, and you can express it all this into a constant, and you can show that the eta burn rate ratio is proportional to G naught to the power of 0.8, and a constant here is always present. So, still two constants are present here. So, having done this, it's at that time we had to make a choice between how to pick two constants and so on. I had done a project much earlier on erosive burning of homogeneous propellants and determined the constant alpha and beta. I must tell you, I was quite unhappy with the numbers which we obtained. It was not very consistent. So, for a variety of reasons, I was displeased with the unsettled situation about erosive burning. So, it was clear, of course, the burning rate ratio is crucial, and so is the mass flux. That is the time when you look at the data which was available, and we know that G naught is crucial. So, plot eta versus G naught first. Let us see what happens. There is a complex dependence because of e to the power of minus beta eta naught and so on. Let us say at the moment there are some compensating features. Nature sometimes is more helpful than what we think. We can infer that it is so complex, but let us assume it is not so complex and see what happens. Just a hypothesis. So, you plot eta versus G naught essentially. This is essentially, in this particular case, is just G naught. You will discover everything seems to be falling into this. So, you do not need to complicate the expression with all this and include a coefficient and so on. And also that coefficient settles on its own, and so that the log which you see here comes out like when you cook, you put various ingredients and stir, and suddenly you will get the food available. So, it is something like that. There is not too much that has to be done. Key thing is to plot the experimental data consistently and carefully in this mode. Okay. Now, in one case you see this expression had some Reynolds number effect. So, say okay, let us see, maybe there is a Reynolds number effect, and you will see here I have plotted that with respect to a quantity with 0.125 and here 0.4. You see the scatter seems to be much more here than here. These 3 points fall away compared to whatever is here, and there is no specificity, it should be only one number or the other. See, it is a scaling law, experiment can be different, and let it be settled by the experiment and not by me. So, that is how this 0.125 is chosen, and if you take the slope of this, you will get this expression G equal to G naught into RE to the power of by 1000 to the power of minus 0.125, and some constant here that comes from the slope of this line, and that there is a threshold flux beyond which it begins to operate. That is what this number is. So, you discover that all constants are removed, and the whole thing, there is no constant which is free, it is just a law expressed by nature, and so you accept it. That is how it has. In fact, I have been asked several times a question, how do you know 35 is right? See, it is not me telling some 35 is right or 45 is right, it is what data is showing. You are welcome to choose at 38 and draw a line, no issues about it. So, if you take 38 instead of 35, the predictions will be slightly different, but not awfully different, because erosive burning is something which influences the pressure time curve in the early part of the burn time. So, you must remember the port in a high density propellant grain, the port is smallest in the beginning. So, the fluxes are much higher in the beginning. So, the influence of erosive burning is much more in the early part. That is why I said the pressure time curve will show a longer tail only in the beginning. Afterwards, you may find influence of it in the pressure time curve, but it is not there much beyond. So, it is that you accept this, and I told you the story of what happened with non-axisymmetric grains and so on, and that is what it is. But if you look at the comparison of the physics here, and that in hybrid rocket, you have a fuel grain, you have bound layer, you have velocity profile as you know, you have temperature profile which is like this, flame being where it is, concentration profile, diffusion flame, therefore oxidizer in the outer part and fuel and products are in the inner part, oxidizer and products in the outer part, fuel and products are in the inner part, and this is a diffusion flame. And in a strong diffusion flame, chemistry is very fast compared to diffusion, that is why it is thin, arguments like you have heard earlier. Therefore, the burn rate is controlled by diffusion rate, which is affected by boundary layer next to the regressing fuel surface. To obtain the dependence of the burn rate, flux and flow, velocity and thermochemical parameters, we use what is called Reynolds analogy. If you look at the heat balance to the surface, rho p r dot delta Hs, that the flux coming off from the surface is equal to the heat flux coming from the gas phase k dt dy. I can, please follow this algebra a little more carefully. I can express this as k dt by du into du dy, and so dt I express this as dTf minus Ts, du goes from 0 to u, therefore k into Tf minus Ts by u. I will add a 1 by mu and add a mu here, and there is a du dy. Okay. U du dy is essentially shear stress. So, I also rearrange this, I will add a k by Cp and add a Cp here. So, I get a k by Cp mu, this 1 by mu is here, no, the same mu which is here, and Cp Tf minus Ts divided by u which is here, and you multiply by tau w. Okay. I can rearrange it in the next step, and you will discover finally k by Cp mu, which is essentially mu Cp by k is essentially Prandtl number, 1 by Prandtl number, Cp Tf minus Ts, and I will introduce what is called Cf by Cf naught into Cf naught by 2 into rho u, and the Cf naught is introduced to account for the blowing effect which I spoke to you a few minutes ago, Cf by Cf naught. From this, if you do the algebra, you will get 1 by Prandtl number, and you divide and multiply by delta Hs, you will get essentially transfer number, which is what is put together, rho u, which is present continuously in all this in this discussion, rho u here you see here same rho u, and so it goes into the simple expression of C naught log of 1 plus b into g power 0.8. This result is not very different from what Lenoir and Robillard said. he only added the non-erosive burn rate along with that. So, the physics is about the same, and there are many issues related to B. I do not think we need to discuss it here, but they have similar dependence on Reynolds number or mass flux. This is something that we need to keep in mind. That is all I want to tell you in response to your question. And should you wish to raise any questions on this or anything else, any other question, you are most welcome. We will debate them now.